Hi guys, it's Varnaz, and now we are going to run through exam 1 of 2011. And let's start with question number 1. Now question number 1 is, again, something that is very important and I cannot possibly stress any more, is resonance. Now here you want to arrange these three molecules based on their resonance stability. To do that, we need to draw out their resonance structures. So this molecule 1 here has resonance structures of this, and to do that we are just pushing up those electrons. This second molecule has resonance structure one, and a second resonance structure when you move these lone pairs on the nitrogen, and it pushes up again. Now, when drawing your resonance structures on exams, do not forget to calculate formal charge, because you will get points off for that. And molecule number 3 has resonance structures and now notice I'm doing a very important thing. When I am moving these electrons here and moving these electrons here, this is not a resonance structure because you are exceeding the octet rule right over there. When you're drawing a resonance structure, although it is resonance, you cannot exceed the octet rule. So that is very bad. So now we have a molecule with 1 resonance structure and 2 molecules with 2 resonance structures. This first molecule is going to be the least stable because it has the least resonance. So we can remove these choices. Now to determine between 2 and 3, let's look at the resonance structures themselves and see which one has resonance structures that are the most stable. Whoops. Now, if we look here and here, we will see that we have formal charges. In this top one, we have a formal charge of positive on the nitrogen, and in the bottom one we have a formal charge of positive on the oxygen. Now we know based on our periodic table of electronegativity, oxygen is more electronegative than nitrogen, so oxygen would not want to have a positive charge. So this would be more stable than this, because the nitrogen is happier with the positive charge than the oxygen. So that is answer choice B. Okay. Now this question is again something that we have learned in general chemistry, and you are looking at a reaction and you want to be able to analyze a graph that looks like this. So going through the choices, energy difference 1 is related to the rate of the reaction, and we know that is correct because the rate of the reaction is going from the products to the top, which is the activation energy. So that is correct. Energy difference 2 is related to the equilibrium constant. Now the equilibrium constant is the products minus the reactants. So here's your products, and there's your reactants, and that's 2. So that is correct. Energy of the reactants R is decreased, the reaction will go faster. Now if we decrease this, so let's draw this new You bring your R here. Now, we just went over in answer number 1 what this hump going from the reactants to the top means. It means the rate of the reaction. Now, if you're increasing the rate of that reaction, see how much farther up that is? Your reaction will actually go slower, so that is false. So your answer is D. And moving on. This question is actually pretty tricky, but we shall run through it. And you want to find which molecules are identical. We shall change the answer choices to match it up with the malic acid. So if we start with the first one, we want to make A have the same general structure as the malic acid. So let's redraw. Now, when doing this, wedges and dashes are really important, so don't forget to keep that stereochemistry. So you see that on your OH is coming from the third carbon on the left-hand side. So to make this look like that, we're going to draw the mirror image of it. We're going to flip it to get the stereo, not necessarily the stereochemistry, but the look of the molecule in space the same. Okay. Now this is very important over there, and it's going to be here, but now since you're taking a mirror image, that wedge is now going to be a dash. If you didn't learn about this yet in class, then it's probably not going to be on the exam, but I'm going to run through it to be safe. Now, this molecule, again, you want to flip it on, well, on the wrong mirror image, you're going to want to flip it down on this axis. So continue with this. Okay, now again, pay notice to the wedges and dashes. When you flip this down, you're also going to change the stereochemistry. So this is your Ml malic acid. So that is your answer choice. This is another concept that is from general chemistry, and it has to do with one of those very annoying acid-base equations that I am going to simplify for you. When you see something like this, you're going to think of pH is less than pKa. You have the protonated species. When pH is greater than the pKa, you have the unprotonated species. And this means protonated, the proton is attached to the molecule. Unprotonated, the proton is free floating. So you have a pH of 3 and a pK of 4.2. And we know pH is less than the pKa. So this is going to be in the protonated species, and the protonated species is the one that it's attached to. Now, let's compare the second one to the pH. So you have a pH of 3.0, which is less than a pK of 9.76. So again, you're going to be in the protonated species, so your answer is going to be 1 and 3. Now they give you a structure and you want to figure out the geometry of it, I would recommend you writing this on your card. But before we start with the geometry, we're going to add on any lone pairs or hidden hydrogens. And you could find that by determining the formal charge. Your nitrogen, your atom, you have this. These lone pairs are going to be very bulky and very negative, and they're going to repel these bonded electrons, causing this nitrogen to have an angular stereochem. Okay, well, this nitrogen, now it is not going to be trigonal pyramidal, because let's draw that nitrogen again. And a trigonal pyramidal shape would be like this. So, not trigonal pyramidal. Now, we're going to look at the lone pairs here, and let's zoom in on that, and it's going to look like this. Again, you have your lone pairs, very bulky, very negative, repelling, so you're going to have an angular molecule. When you see something that's oxygen, I always like to refer back to H2O to see how that stereochem, how that molecule relates to water. Now, this is something that is very, very important, is knowing your different functional groups, and we're going to run through this pretty quickly because I hope you know this by now. If not, there's an echo of the review session on Blackboard, and the reviewer did an excellent job going through the functional groups. So this is our carboxylic acid, and I do not see a carboxylic acid in the molecule, but let's run through the other ones. You have an alcohol, and it's pretty obvious you have many alcohols in here. You have your ketone. Now, in the previous video I did for 2012, I did run through what a carbonyl is, but let me run through that one more time because the video was messed up by that unsightly watermark. So you have ketones and you have aldehydes. So ketones, middle, aldehydes, end, and so it will look like this. This is a hydrogen. So ketone, you want to look for that carbonyl in the middle, and we can see one right over there. An ester is a combination of two different molecules. It's an ether and a carbonyl, so it looks like this. So here is your carbonyl and here is your ether, and we have a molecule like that right over here. An amine, remember not to confuse an amine with an amide. An amine is just N, H, or R groups connected to three different things. And that is right there. And a methyl group is just a single carbon coming off an R group. So we have methyls here, and methyls here, methyls here, methyls there. You have a methyl there. So you have a lot of methyls, so we know your answer is carboxylic acid. Hybridization. Now, when you're looking for hybridization, you want to see how many atoms or how many lone pairs your molecule of interest is attached to, and it has nothing to do with the type of bond, so you ignore if it's a double bond and you ignore if it's a triple bond. So you're just going to count how many things it's attached to. So this carbon number 1 is attached to 1, 2, 3 different things. So that is 3 minus 1 equals 2. So that carbon is going to be sp2 hybridized. This carbon over here, you would assume that it's only attached to 3 different things because you could only see it attached to 3 things. But there is that dreaded hidden hydrogen. So carbon number 2 is actually attached to 4 things. So it's attached to the hydrogen, the carbon of the carbonyl, the methyl group, and the ring. Minus 1 equals an sp3 hybridized. So you're going to be answer choice C, sp2, sp3. And we're going to skip number 9 since that is chapter 3. And that is not going to be on your exam. And we're going to skip number 10 since this is a synthesis and it's not going to be on your exam. 11 is IR, and again, not on the exam. But let's look at this one here. I'm not sure if this is on your exam or not, but we're going to run through it anyways. And it does tie in a lot with resonance. So it wants us to know which 2 hydrogens in this molecule are the most acidic. And we know something that is acidic accepts electrons and donates protons. So what it means when donating a proton is if you pluck that proton off and that proton donates its lone pairs, will that molecule be happy with that extra set of lone pairs? So let's start with here. Let's, for instance, look at this hydrogen. If you take that hydrogen and you pluck off and you donate the lone pairs, that carbon is not going to be very happy with its negative charge. But here we have something that's very interesting. We have our ester. Now, again, as we said, the carbon coming off of a carbonyl directly attached has very acidic hydrogens. And let's draw this out to give a more visual representation. If you remove these hydrogens and you donate your lone pairs, you are going to be able to resonate with that carbonyl. So since you have resonance, your negative charge is going to be delocalized, and this molecule will be able to handle that negative charge more easily. So we have an acidic hydrogen over here. Now let's look at this hydrogen here. It's again very interesting. If you donate, you have a lone pair. If you donate those electrons, you're going to have a 1, 2, 3, 4, 5, 6 negative formal charge. Now, nitrogen is more, how to phrase this correctly. Nitrogen handles a negative charge or any charge better than a carbon. So you know this hydrogen here is going to be more acidic. It will be happier with that negative charge than this carbon here if you pluck off that hydrogen, because as I'm sure it has been beat into your head multiple times and you're tired of hearing it, never ever 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 give carbon a charge. So these are your 2 most acidic hydrogens. Okay. Draw the product of the following reaction. This is called a deuterium exchange. Whenever you see these reactants, know it's a deuterium exchange. You really do not need to know the mechanism to the best of my knowledge, but if you want, I'm positive that it's in the textbook, or you could find it online and look at it. What this does, it replaces acidic hydrogens with deuteriums. And as we went over in the previous question, hydrogens that are attached to the carbon that is directly attached to the carbon of the carbonyl, so this 1, 2 coming off has very acidic hydrogens. Now you could tell me, but wait, I don't see a hydrogen there. But you have your hidden hydrogen right over there. So this is the most acidic hydrogen, and it is actually the only acidic hydrogen in the molecule. If you had more than one acidic hydrogen, then you will replace more than one hydrogen with a D, with the deuterium. So your final answer, that's a D, will be this. Okay. So I think solubility is actually in chapter 3, but we shall run through it anyways because it gives us good practice with drawing our molecules and practice on how to look at the equation of a molecule and be able to draw its possible structures. So we have 3 carbons, 9 hydrogens, and 1 nitrogen. Now, there is something called the IHD formula that Tim did go over in the review. You have not learned it yet. It is useful, but is not necessary to. So we shall go through our different choices, and we have this. Now, label your hydrogens. I'm going to draw blue dashes for my hydrogens. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 1 nitrogen and 3 carbons. So this is a possible structure. Now, what would happen if we moved that nitrogen elsewhere? So let's move the nitrogen in the middle. And it's going to have 1 hydrogen here and a lone pair. Now let's count. So you have 3 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens, and 1 nitrogen. So this is a possible structure. And basically, we're just going to go through and continue drawing these structures. And the next possible structure that we have is NH2. And to do these, you really need a lot of practice on drawing these molecules. It's very simple once you get a hang of it. You have to make sure you take into account formal charge. If you don't see a formal charge given, or the molecule does not have an overall charge in the equation, then you shall not have a charge in the choices that you draw. So these are the choices that we draw, and you want to know which one is, if you could read through that, is least soluble. The cool thing with amides is this general rule: the more substituted the amide, the less soluble it is. And what I mean with more substituted, when you look at the amide functional group, you have possibility of having these R groups and hydrogen. These R groups here can also be hydrogens. So this is going to have 2 substituted groups because it has 2 R groups. But if this is a hydrogen, this is least substituted because it only has 1 R group. So if we follow by that rule, if you understood that, you have 1, 2, 3 substituted. So this is the most substituted amine, and that is going to be your final answer. Sorry, I was experiencing some technical difficulties, so let's start with question number 15, drawing resonance. So remember, with resonance, you cannot change the connectivity. The only thing you can change is the flow of your electrons, since resonance is basically different portrayals of the same molecule. You can only mess with the lone pairs, the pi bonds, which are basically wherever you have a double bond or a triple bond, those are pi bonds. You cannot move a single bond because a single bond is your s orbital, and You can't move those electrons in the s orbital. So I'm going to start off with moving the electrons in that pi bond up, and this is where practice with redrawing molecules comes in handy. And if you feel like you are not comfortable with redrawing a molecule, please number your carbons, and that will prevent any silly redrawing mistakes. So I have my nitrogen, 1, 2, 3 carbon, 1, 2, 3 carbon, and that is going to have a negative charge, and this is a positive charge, and that is a hydrogen, not a methyl group. Next, I want to, for my next resonance structure, I want to pay attention to the lone pairs on that nitrogen. That lone pair is going to be donated to the bond right next to it, and it's going to shift that double bonded electrons, so those pi electrons, into this bond over here. So just follow the arrows, draw your arrows so you know where what is going, and it's going to be easier when you are redrawing your molecule. So you got rid of that positive charge by shifting the electrons. Your nitrogen is getting a positive charge because it donated its electrons. And this carbon see, I forgot to follow the flow of my electrons. Okay, this nitrogen is getting a positive charge. This carbon is neutral because it's bonded to 3 things, and this carbon is also neutral because it is bonded to 4 things, and this carbon is also neutral because it has 4 bonds. They have a full octet. So those are your charges, and you want to see which one, structure A or structure B, is a better resonance structure. Now, let's look at this. Let's look first at the charges that are present. And these two molecules both have negative charges on the oxygens, so you know that is not a good determining factor. But let's look at where the difference in the positive charges are. Here you have a positive charge on a nitrogen, and here you have a positive charge on a carbon. You know, hopefully by now, by the countless times that it has been beat into your head, that having a charge on a carbon is never good. That majority of the time, when you have a positive or a negative charge on a carbon, it is going to be the least ideal resonance structure. So choice B, even though you have a positive charge on your nitrogen, is going to be better. And that is going to be the conclusion of this video.